In the next few videos, we'll see how to find a shortest path in a weighted graph. This problem appears often in everyday situations, from routing car traffic to routing internet traffic. So how does a weighted graph differ from a regular graph? Well, in a weighted graph, every edge has an associated numerical value. So this is called the weight of the edge, and it could be anything. This could be distance, this could represent cost, so this could be some dollar value, which is either positive or negative. So in a weighted graph, every edge has some weight, which is just some numerical value which is associated with it. For example, in this flight graph, the weight of an edge represents the distance in miles between airports. So between SFO and ORD airport, there's 1,843 miles. Now, given a weighted graph and two vertices, we want to find a shortest path between them. Now, you've solved the shortest path problem before in an unweighted graph when there were no weights associated with edges. In effect, that meant that every edge had basically the same weight. But now that we have weights associated with edges, we want to find a path of minimum total weight between U and V. So the length of a path in a weighted graph is the sum of the weights of its edges. So for example, if we have here, let's say vertex A, B, C, and D, and a weight associated with each edge, let's say this is 3, 5, and 2, then the length of this path is 10. This is 3 plus 5 plus 2. Versus, let's look at a different path now. Let's say we had another vertex, E, and here 15 and 15. So the weight of the bottom path from A to D is 10, but the weight of the top path is 30. So the shortest path from A to D in this graph is this bottom one here, which has a total weight of only 10. Notice that this isn't the same thing as finding a path that has the least number of edges. In this case, a shortest path uses more edges than this other path, which uses less edges. In an unweighted graph, finding a shortest path is the same as finding a path that uses the least number of edges, since all edges effectively have the same weight. But when we're working with a weighted graph, we can't just find a path that has the least number of edges. We need a better way of finding a shortest path, because the shortest path might not have the least number of edges, since this is based on the total weight of edges along that path. Okay, so for that reason, we can't use what we had seen before, which was breadth first search, in order to solve this problem. We need a different approach. Now, finding a shortest path, this is effectively what your phone GPS does when it maps the most efficient route in order to get from your current location to another. This is also used in internet packet routing. So a message can be sent from point A to point B along many routes, but you want to choose the one which incurs the least delay so that it arrives as quickly as possible. So for example, in this flight route network, we have a shortest path from HNL airport to PVD airport goes exactly through these vertices, through these airports, following these edges. So a couple properties we have for shortest paths. One is that any subpath of a shortest path is also a shortest path. So this means that if we know already between these vertices, let's say U and V, we have a shortest path. Maybe it goes through these edges exactly, which for the moment I'm just not labeling what the weight associated with each edge is. If we knew already that this was the shortest path, then any part of this path is also shortest. So that means that, let's say from here to this vertex is the shortest path through this edge. This is the shortest path because it's a subpath of an even larger shortest path. We know this must be shortest because otherwise, if it wasn't, we could replace it with something which is even shorter. Let's say this is vertex T. We would replace it with an even shorter U to T path, which would ultimately give us an even shorter U to V path through T, contradicting that we had started off with UV being a shortest path to begin with. So any one of these subpaths, if we were to go from U to this vertex, or pick only from U to this vertex, any possible shortest path, where this just represents a subpath of vertices and edges along this path, those are all shortest paths as well. So this means that there's a tree of shortest paths from a start vertex to all other vertices. Why must such a tree exist? The reason is that if the shortest path from vertex S, to vertex T goes through some intermediate vertex V, then that means that this is also a shortest path from S to V as well. So every vertex other than S can be assigned some parent. Namely, this is the second to last vertex in the path. So for example, if this was our path shortest path from S to T, then we could assign the parent of T is this vertex, the parent of V is this vertex is V, the parent of this vertex is this one, the parent of this vertex is this one. And we do this for every vertex. So we find a shortest path from our starting vertex to some other far away vertex. We know that any subpath of that shortest path is also a shortest path. So by finding a shortest path from S to T, we also find a shortest path from S to any other vertex along the way. And if there's any other vertex that we still have to find a shortest path to, then we find a shortest path to it, and we find a shortest path as a consequence to all of the other vertices along the way to that vertex. So this creates a tree. For example, in this flight network, we have a shortest path tree, which is rooted at PVD airport. And this gives us a shortest path from PVD to every other vertex in this graph, following only those edges which are in red. So this gives us the shortest path from PVD to HNL along this path, which also gives a shortest path from PVD to LAX, and also from PVD to ORD. And the first algorithm for today, called Dijkstra's algorithm, builds this shortest path tree outwards from the starting vertex in a greedy fashion. So this will compute the distances of all vertices from a given start vertex S. So the goal is to find the shortest path tree rooted at vertex S, which will give us the shortest path from this single starting point, from this single source vertex S, to every other vertex in the graph. Now, in order to apply Dijkstra's algorithm, we're going to assume already that the graph we're working with is connected, and that the edge weights are all non-negative. That means that they're greater than or equal to 0. So we won't be able to apply Dijkstra's algorithm if there are negative edge weights, and you'll see why in the next video. But the idea behind Dijkstra's algorithm is that it will grow a cloud of vertices, beginning with that initial start vertex S, and eventually cover all vertices, so that we form in this cloud, as we encounter vertices next through some edge, we maintain that a shortest path tree of every vertex which is in this cloud so far. Now, how we build up this cloud is with a greedy approach. So we'll store with every vertex a distance label. So vertex V has distance label here D, which represents the distance of V from our starting vertex S. Now we'll update this as we go along if we find kind of a better way to get to V. When we're finished with Dijkstra's algorithm, we'll have appropriately set the distance label to all vertices and maintain a shortest path tree rooted at vertex S. And at each iteration of Dijkstra's algorithm, we'll add a vertex to the cloud. Now, how we add a vertex is based on its distance label. So of all of the vertices which aren't in the cloud yet, we'll pick whichever one has the smallest distance label. Let's say that's vertex U. We'll add this vertex to the cloud, and we'll do what's called an edge relaxation step. So this is that for that vertex U added into the cloud, we'll update the labels of the vertices adjacent to that new vertex U added to the cloud. So this is called an edge relaxation. So let's say we had this edge E, to give an example of how we relax edges. Let's say we are relaxing this edge E, And suppose before we had gotten to this point that we had already set a distance label for z to be 75. So perhaps this was realized by this path through some other vertex here. Maybe this has a distance label of, let's say 40, which means it took 40 steps to get from S to this vertex, and the weight of this edge was 35. So this is one way that we could have gotten a distance label of 75 here at vertex Z. But at this moment in time, we're currently adding this vertex U to the cloud, meaning this has the next smallest distance label of all other vertices not in the cloud just yet. So after adding this vertex that has the smallest distance label to the cloud, we relax all incident edges. So when this edge is relaxed, we check to see, is there a better way to get to Z using this edge other than using however way we had to get to Z before? So we're going to update this distance label based on two things. So the new distance label during this edge relaxation step will be the smaller value of whatever was stored in Z before. Maybe we had already found a shorter path to Z and we don't want to use this edge. Or this edge gives us an even shorter path, and the length of that path is however much it costs to get to vertex U plus however much it costs to go through this edge. So this gives us one possible path in which we can get to Z. We just want to figure out if the length of that path is better than what we had before. So in this case, it is. We have 50 steps to get to U plus 10 steps to get through this edge E, since this is the weight of that edge. And our resulting value is 60, which is better than what we had before. So when we relax this edge, we update the distance value for Z, because now we've got a better way to get to Z through this edge. And we can indicate now that, kind of by marking this edge or assigning a parent to Z, that this was the edge that we took to get to Z in order to get this value, and we didn't use this other edge instead. So this is called edge relaxation. We're relaxing this edge E, and we're evaluating whether we can update this distance label appropriately. So let me show you first an example of running Dijkstra's algorithm, and then in the next video we'll analyze the full algorithm. So let's say this is the starting graph. And let's say that we want to find a shortest path tree rooted at A, meaning we want to find a shortest path from A to every other vertex in the graph. So Dijkstra's works on a labeling scheme. So initially, since we want to begin with A, we're going to set its distance label to be 0, because the distance to itself is 0. And for everything else, we're not sure yet, so we'll assign it to be initially infinity, or integer max. And Dijkstra's algorithm will work by grabbing whichever vertex isn't in the cloud that has the smallest distance label. So in order to indicate which vertices are in the cloud, I'm going to use this notation, just a circle around a vertex to show that it's that vertex is in the cloud. So initially, the only vertex that has the smallest distance label is A, so this will be the first one in the cloud. Now we're going to relax each edge incident to this vertex which we just added to the cloud. And remember, when we relax an edge, let's say we're relaxing the edge from vertex U to Z, supposing that we just added U to our cloud. Let's draw it this way. So this is a cloud of vertices. When this edge is relaxed, we update Z's distance label. So we set the distance label for Z to be the better of two possible values. So this distance label is representing the best way that we had to get from whatever our starting vertex in the cloud was to this vertex Z. So either we could go through vertex U or we don't. We keep whatever shortest path we had before. So in that case, the length of that path, or the distance, was the distance label for Z. Or if we find an even better path that goes through U, then the length of that path would be however much it costs to get to U, which is the distance label of U, plus however much it costs to go from U to Z. So if this is edge E, then let's say this is the weight W of that edge E. So this is how we'll relax each edge incident to a vertex that has just been added to the cloud. So right now A is the only vertex that's been added to the cloud. we'll relax each of these 3 edges. So let's start with the one on the left. When this edge is relaxed, we find that B's distance label can be updated to be 8. This is better than what we had before, and right now this edge is giving that shortest path so far that we found to B. When this edge is relaxed, we can update C's distance label to be 2. And when this edge is relaxed, we can update D's distance label to be 4. Okay, now of the remaining vertices that haven't been inserted in the cloud, we take whichever one has the smallest distance label, which is uniquely C, and we'll add it to the cloud. Now that C is added to the cloud, all edges incident to it are relaxed. So of each of these edges, we'll relax them. So we've got here on the left, using C as an intermediate vertex, we can now get to B in a total of 9 steps. This is the 2 steps it took to get to C, so the distance label of C, plus the 7 steps it took to get from C to B. And this isn't any better than what we had before, because we could already get to B in 8 steps. So to indicate that we're not using this edge, but we've already considered it, I'm going to use a dashed line. Now let's look at the next edge. When this is relaxed, we find that we can get to E in a total of 5 steps. This is the 2 steps to get to C plus 3 steps to follow this edge. We'll update our distance label here. And when this edge from C to F is relaxed, we find that we can now get to F in a total of 11 steps. The 2 steps to get to C plus the 9 steps to get to F. And lastly, we'll relax this edge to D. We find that C does give a better path because we can now get to D in a total of 3 steps, and this is better than what we had before. So to indicate that now this edge is being used rather than this one, I'm going to cross this one off. Algorithmically, we can do this by recording with each vertex a parent of what vertex gave a better, shorter path. So for example, if we do update a vertex, its distance label, then we'll record Z's parent to be U, for example. Okay, so now that all incident edges to C have been relaxed, we'll add the next vertex, which isn't in the cloud, which right now only consists of vertices not in the cloud are B, E, F, and D. And take whichever one has the smallest distance label, which is D. So now D is added to the cloud, and we relax this only incident edge. And we find that we can get to F, even better, we can get to F in 8 steps. This is the 3 steps it took to get to D, which we recorded already, plus another 5 steps to get from D to F. So since this gives a better route, we'll update F's distance label and indicate that this edge is no longer being used to get to F. We used this better edge instead. Of the remaining 3 vertices, we take whichever one has the smallest distance label, which is E, we add it to the cloud, and relax all incident edges. So when this edge is relaxed, B's distance label gets updated to be now 7. We can get to B in 7 steps by first going to E, which takes a total of 5 steps, and then another 2 steps to get from E to B. Now of the remaining 2 vertices, we take whichever one has the smallest distance label, which is B, and we relax all edges, although at this point we have no other edges that in order to relax. And then again for F. So this is our resulting spanning tree. If we take only those edges that are bold and not the ones which I've crossed off, which gives, I claim, a shortest path tree rooted at vertex vertex A. So we have a shortest path, now that we're not using this edge, we have a shortest path from A to B, which follows this path from A to C, and then C to E, and E to B, for a total of, we got 7 steps. We have a shortest path from A to E then, and also A to C, and from A to D, and A to F. In order to prove that this actually works, and I'm not just making it up here, in the next video, we're going to see why this strategy, which this is a greedy method because we're always choosing the next vertex that has the smallest distance label in order to include it in the cloud. As a greedy method, we have to demonstrate that this has the greedy choice property. So why is it the case that if we pick a vertex that has the smallest distance label, add it to the cloud, and appropriately update distance labels in this way with an edge relaxation step, why does that guarantee that as long as our graph has non-negative edge weights, that it will actually come up with a correct shortest path tree? So you'll see that in the next video.